You think falling into a black hole would kill you instantly. Flash of light, violent end. The universe closes around you, and that's it. That's not what physics says. And the real answer, what the equations actually predict, is considerably stranger and considerably more disturbing than instant death. Because from your perspective, crossing the event horizon of a large black hole feels like nothing. No wall, no heat, no alarm. You cross the boundary between the universe and the inside of a black hole, and you don't feel it. You might not even know it happened. And then, only then, does the problem start. Let me back up, because there's something almost everyone gets wrong about black holes before we even get to what's inside them. Black holes don't suck. I mean that literally. They don't pull things in like some cosmic vacuum cleaner. If you took our Sun and replaced it, right now, same mass, with a black hole of identical mass, Earth would keep orbiting exactly as it does today. Nothing would be sucked anywhere. The planets would continue on their paths. The gravitational field at any given distance would be identical to what it is from the Sun. The difference is simple. From a normal star, you can eventually escape if you move fast enough. From a black hole, beyond a certain distance, you cannot, because the speed you'd need to escape exceeds the speed of light, and nothing moves faster than light. That boundary, the point where escape velocity equals light speed, is the event horizon. It's not a physical surface. You can't touch it, see it, or feel it. It's a mathematical boundary defined by geometry, a line drawn by the equations of general relativity that says, past here, all paths lead inward. And here's the part that should unsettle you. For a sufficiently massive black hole, a supermassive one, the kind that sit at the centers of galaxies, the tidal forces at the event horizon are actually quite gentle. Stretched over such an enormous radius, the difference in gravitational pull between your head and your feet at the moment of crossing is small, survivable. So you cross, you feel nothing unusual. You're inside a black hole and you don't know it. Now let's talk about what happens next. Inside the event horizon, something fundamental about the geometry of space-time has changed. Outside, space and time work the way we're used to. You can move forward or backward through space, but you move in only one direction through time. Forward, always forward. Inside the event horizon, the radial direction, the direction pointing toward the center, becomes time-like. What that means, stripped of jargon, is this. Moving toward the singularity at the center is not moving through space anymore. It's moving through time. And just as you cannot stop time, you cannot stop moving toward the singularity. It's not in front of you in space, it's in your future, structurally, unavoidably. No engine, no thrust, no force in the universe can prevent it. Because preventing it would require moving backwards in time, and that's not something the universe permits. Now, the outside universe doesn't disappear. From inside, you can still look out, for a while. And if you do, you see something extraordinary. The light from the entire future of the universe outside is pouring in through the shrinking cone of sky above you. You'd see billions of years of cosmic history compressed into your final moments. Stars being born and dying, galaxies evolving, the long, slow cooling of the universe, all of it visible, accelerated, streaming in. I find that remarkable. Not comforting exactly, but remarkable. Now, the question of what actually kills you and when, it depends on the size. For a stellar mass black hole, the kind formed when a single massive star collapses, the event horizon is small, maybe a few kilometers across. At that scale, tidal forces are extreme even at the horizon. The gravity pulling on your feet is measurably, violently stronger than the gravity pulling on your head. You get stretched, lengthened along the radial direction, compressed from the sides. The process has a name. Physicists called it spaghettification. They named it that deliberately, And I think that's one of the more honest moments in the history of naming things. You become a long, thin stream of particles before you've even crossed in. But for a supermassive black hole, billions of solar masses, the event horizon spans millions of kilometers. At that scale, the tidal difference is gentle at the crossing point. You survive it. The spaghettification only becomes lethal deep inside, well past the horizon, as you approach the singularity. Either way, eventually you reach it. And here is where I have to be honest with you in a way that most explanations aren't. At the singularity, the equations break. General relativity, the theory that describes everything I've just told you with extraordinary precision, predicts infinite density and infinite curvature at the singularity. It produces infinities. And in physics, when your best theory produces an infinity as an answer, that infinity is not a physical prediction. It's a signal. It means the theory has reached the edge of its own validity. It's telling you, past here, I don't know. This is not a flaw being hidden. Every physicist working on this knows it. The singularity is where general relativity runs out. Something else takes over. Something involving quantum mechanics, which governs the behavior of matter at the smallest scales. And we don't have a complete theory that combines quantum mechanics and general relativity. We have attempts, we have candidates, we have brilliant ideas that might be right. We don't have the answer. The singularity is not a physical point of infinite density. It's almost certainly a signal that our description of spacetime breaks down at extreme enough scales and densities. What actually happens there, whether spacetime ends, whether it bounces, whether something stranger occurs, we genuinely don't know. And I want to be precise about what "don't know" means here. It doesn't mean we have no ideas. It means we have competing ideas and no experiment to test them. Loop quantum gravity predicts the collapse bounces, that the singularity is replaced by a quantum bounce and matter re-expands. String theory suggests other structures. There are others. None have been confirmed. That's the honest position. Now, there's one more piece of this that changes everything. Stephen Hawking showed in 1974 that black holes aren't completely black. They radiate. The mechanism comes from quantum mechanics. Near the event horizon, pairs of virtual particles constantly form from the vacuum, a particle and its antiparticle created together, existing briefly. Normally, they annihilate each other and return their energy. But near the horizon, occasionally, one falls in while the other escapes. The escaping particle carries real energy. From a distance, the black hole appears to glow, faintly, unimaginably faintly, with what's now called Hawking radiation. The temperature of this radiation for a stellar black hole is a fraction of a billionth of a Kelvin, far colder than the cosmic microwave background radiation that fills the universe, completely undetectable with current technology. But the principle matters, because it means black holes lose mass over time, and over timescales so vast they make the current age of the universe, 13.8 billion years, look like nothing. Every black hole eventually evaporates completely. And this is where we arrive at the most troubling open question in theoretical physics. When a black hole evaporates, what happened to all the information about everything that fell in? You. Every particle of matter, every quantum state, every piece of information about the structure of everything that crossed the event horizon, where did it go? Quantum mechanics says information cannot be destroyed. This is not a preference or a philosophical position. It's a mathematical property of quantum theory. The laws of physics are time reversible at the quantum level. Information is conserved. But if a black hole forms, swallows things, and then completely evaporates, emitting only this faint thermal radiation that carries no specific information about what fell in, then that information appears to be gone, destroyed. These two things cannot both be true. Either quantum mechanics is wrong about information conservation, or Hawking radiation carries the information somehow, or there's something else entirely going on that we haven't understood yet. Hawking spent decades wrestling with this. He initially argued information was destroyed. He later changed his position and argued it was preserved. The debate is still active. No resolution has been agreed upon by the physics community. I predicted antimatter from an equation before anyone had seen it. I wrote down a relativistic equation for the electron, and the mathematics told me there had to be a mirror particle. Same mass, opposite charge. Everyone thought it was a mathematical artifact. Then Carl Anderson found it in a cloud chamber in 1932. The math was right. The universe confirmed it. I believe the mathematics of black holes is right too. What the mathematics is telling us about the singularity, about information, about what space-time is at the deepest level, that's what we haven't figured out yet. Not because the universe is hiding it, because we haven't found the right way to ask the question. Black holes sit at the center of almost every large galaxy. The one at the center of ours, Sagittarius A star, has a mass of 4 million suns, and it's sitting there right now, about 26,000 light years away, a permanent presence. It's not threatening. It's not consuming the galaxy. It's just sitting there, curving space-time, holding its secrets, waiting for us to figure out the right equations. And here is what I find genuinely extraordinary about all of this. A black hole might not just be a region where things fall in and disappear. There's a serious proposal, the holographic principle, which suggests that all the information about everything inside a black hole is encoded on its event horizon, not stored inside, on the surface. The entire three-dimensional interior described completely by information on a two-dimensional boundary. If that's right, it has implications that go far beyond black holes. It suggests that the universe itself, everything we experience as three-dimensional space, might be a kind of projection from a lower dimensional surface. That the depth of space is not fundamental, but emergent. I'm not telling you this is confirmed. It isn't. I'm telling you this is where the physics is pointing, and that the direction it's pointing is stranger and more interesting than anything fiction has imagined. The universe keeps doing this. The closer we look, the less obvious the nature of what we're looking at becomes. Every time we think we've found a solid foundation, the floor turns out to be more interesting than the walls. Black holes are the best example I know of a place where the universe is clearly telling us something important that we haven't understood yet. The job isn't finished, not even close.